My name is Mike Scher. If I could remind everyone to please mute your cell phones if you haven't done so. So it's my pleasure to introduce our speaker tonight, Tom Campbell. And Tom has been collecting minerals since he was 7. So it's been a couple of years. He got his BS in geology from the University of Akron, his master's and postgrad work at the South Dakota School of Mines. He then worked at the Homestake Gold Mine, one of the most productive gold mines in the world. Currently, he is the staff mineralogist for the Arkenstone, and you'll see some brochures up here. They are one of the major sort of fine mineral dealers in the world. Tom is also doing independent exploration consulting work for the gold mining industry. He has a passion for research and interest in granite pegmatites and specializes in their geology and mineralogy, which you're going to hear about. Most of his mineral collection is devoted to common and rare mineral species originating from lithium-cesium-tantalum type granitic pegmatites. He has spent considerable time studying and appreciating Brazilian pegmatites, and he has on his own described 3 new minerals and co-described 8 others which are new to science. In addition, he's the co-author of the 2nd edition of the Encyclopedia of Minerals, published numerous professional papers and in professional journals. I urge all of you at the end of the talk, if you haven't had a chance to look at the minerals on this table over here and over here. If you feel that some of them have to remain in Jackson in your home, talk to Tom. Please, or call me tomorrow. Please join me in welcoming Tom Campbell.
Thanks for the introduction, Mike, and thank you for having me here. And I appreciate the invitation. And Melissa, my wife, and I were we're looking forward to being here. And Mike and Barb were gracious enough to take us on a wonderful hike today. And we love Jackson Hole. I've been here several times in the past, and just a wonderful place. And as far as my talk goes, I'll give you a little bit of an introduction. Kind of like what Mike said. So I love gold geology, and that's pretty much what I do for a living. And part of my career in recent years has transitioned into working for Rob Levinsky at the Arkenstone part-time, and Melissa helps with that too. And it's really it's kind of more of my passion, working for him and being able to study pegmatites. And I've studied pegmatites for just as long as I've studied gold deposits, which is 30-some years. And anyway, so part of what I do for Rob, just to give you an idea, I help him with sales. But the other thing, I help him with respect to mineral acquisitions, and that might be maybe traveling to Europe to attend an auction. You know, maybe an auction house like in Paris or something might have someone's collection, a prominent collection for sale. So I'll go and represent Rob there and try to acquire specimens for Rob for the Arkenstone, evaluating mineral collections and appraising them. And then also helping him with shows like the Munich show, which is coming up in Germany at the end of this month, and then the Tucson show, Denver show, which just happened in September. So those kind of trade shows. And the other thing that I do for him, which I really enjoy, which kind of takes care of a couple things for me, is like going to Brazil. And so when I go to Brazil, I've been doing that for about 10 years, both as part of my iron ore career, which was several years that Melissa and I did, which is where I made my initial contacts, and then which transitioned into pegmatites, actually visiting the pegmatites down there and making contacts there. And so part of that too is visiting people that are now very good friends in Brazil. They're good contacts for minerals, and also visiting the mines that they own, right? So being able to evaluate pegmatites. And, you know, that's something that's really different. It's something that with a lot of you, I know being geologists, you know, we didn't learn how to evaluate like gemstone bearing deposits, you know, when we were in college, right? At least I never did. And so that's a specialty that I've kind of developed over the last several years. So, you know, we can evaluate like oil and gas resources. I can evaluate gold deposits, and evaluating pegmatites for their gemstone or maybe their other economic minerals that they might mine, right? So it's a totally different game than like gold, oil and gas, lead, zinc. Okay, so just to give you kind of a perspective in terms of what I do and how almost kind of specialized that kind of work is, which I really enjoy. So I'll tell you a little bit about some of the stories on my travels to Brazil and whatnot during the course of this. But yeah, I love pegmatites and I love studying them. And my talk tonight, and I like the way, I'm not sure who it was, they did a better job on my title than I did. They said spectacular gem crystal pocket formation and survival. So that's what I should have done, right? Yeah, real attention getter. So anyway, that's what my presentation is on. And let's see, okay. Do I need to be close, or?
The two side arrows.
Yep. Oh, so I'm doing the pointer while I'm doing that, right? Okay. So before I really get into it, as a preface, there's some questions that I thought I'd present, and these are ones that I thought I'd try to answer through the course of this talk. And number one, what are granite pegmatites, and how do they form? What are the differences between a granite and its related pegmatites? What are some of the complex processes that form gem-bearing pegmatites? How old are these gem pocket pegmatites? And what are the minerals that occur in them, especially the kind of gem crystals? And then how common are pegmatite pockets, and do the contents get preserved? Okay. So let's start with kind of a very general definition of a pegmatite. A totally crystalline, generally very coarse-grained, light-colored igneous rock derived from a parent granite, composed mainly of quartz, feldspar, and mica. And the pegmatites, they differ in composition from a granite by their enrichment in sodium, lithium, rubidium, cesium, boron, fluorine, OH, and sometimes beryllium, niobium, tantalum, and tin. And to give you an idea of the size of crystals in pegmatites, this is an outcrop of pegmatite along a road cut in Keystone, South Dakota. And that's my wife for scale. And she's 7 feet tall. Now, some of you have met her already, and you know that's not true. But anyway, the crystal's big, and no, my wife isn't 7 feet tall. But the other thing to appreciate too is the largest crystals in any kind of a deposit are from pegmatites. Okay, so like at the Etta mine, which actually isn't too far from this outcrop that we stopped at years ago, there's a spodumene crystal there that was 14 meters long from the Etta mine, okay? And the largest pegmatite crystal, and actually the largest crystal in the world, is from a pegmatite, and that was from one in Madagascar, and it was a burl crystal that was 18 meters long. We'll talk a little bit more about that later. Yeah, so 18 meters, so that's at least probably about the length of this room, the width of it. So pegmatites supply some of the world's finest colored gemstones, such as tourmaline, topaz, aquamarine, and at least 40 other gem minerals. And they're sources of fabulous mineral specimens and crystals. And that's part of this market that the Arkenstone and many other mineral dealers are in. And so a good portion of their stock comes from pegmatites, okay, around the world. And they're host to a diverse suite of exotic minerals, and they're the only source of many rare minerals. And to give you an idea, Mike talked about discovering 3 new minerals. Well, one of them was tiptopite, and it's a rare and very complex sodium, lithium, beryllium phosphate hydrate, and that's those little white sprays that are in that particular photograph here. So it's these little white sheaves. And then it's associated with rocherite, which is another beryllium phosphate, hurlbutite, another phosphate, and it's on whitlockite. Not that these names mean anything to you. They're very rare and kind of unusual. But under the microscope, these things are beautiful, right? And it's too bad they're not like 10 times that size. But anyway, that was the focus of a lot of my research. But let me tell you a little bit about it, because you hear about people, describing new minerals, or you hear how that, 200 and some minerals were discovered last year, right? Well, and I'm just going to very briefly tell you how it's done in that kind of the process. So part of this, at least at the Tip Top mine, which is in Custer, South Dakota, it ended up being my master's thesis, the work on it. And what happened is that there was an old miner in the Custer area who decided to go back into the Tip Top mine, which was mined previously for beryl, right, as a source of beryllium. And he pumped it out, went back in, started mining in one part of the pegmatite. And, I was a grad student then. I was running around to pegmatites, looking at minerals and seeing if there was anything new and interesting, right? So I'd stop by and see Vern and see if he had anything new and different that he was uncovering here other than the cool big giant beryl crystals. And it turns out that there were these fractures in the beryl and in the feldspar. And yeah, they had these colorful associations in there, right? And I didn't know what they were. And so my advisor and friend and mentor, Bill Roberts, I don't know if you've ever heard of him or ever got a chance to meet him, wonderful man. But he's the one that invited me to work on the encyclopedia with him, revision. And anyway, I was collecting this material and brought it back to him. We started looking at it under the microscope. Okay, so that's the first step. And we're trying to identify these things. And some things, it looks like it could be the red things, it looks like it could be rocherite group mineral. The white spheres, no idea. And these, we were thinking, well, maybe it's this phosphate, maybe it's that one, but it doesn't look right. And so, we've got all of our guesses and we're writing descriptions of them. And then, so the next step is to try to characterize them chemically, right? And even by optical properties. And so the optical portion was my forte, and I also did a bit of analytical work. And so I did some atomic absorption spectroscopy on these. And the process, because you're dealing with very small amounts of material, right? So they're really kind of micro analyses. And so I determined, like the beryllium, lithium, and the phosphate anion. And the other part then too is to at least do as much as we could at the School of Mines, was to do the optics on it, so determine the optical properties of it. And just to give you an idea how complex this is, I don't know if any of you have ever heard of this, the geologists, but we've done refractive indices in lab, and we've looked at things in thin section, and even grain mounts, immersion mounts, and immersion oils, right? So there's this method, and Bill happened to have this tiny little apparatus called a détente spindle stage. okay? So it's almost like a protractor that's bent up, and it has almost like a paper clip running through it, okay? And it has little angles on there, you know, marked out on the protractor part of it. And you actually, get this, you glue one of these 2 or 3 millimeter crystals on to the end of this part of the paper clip, right? And you put it in different refractive index oils until you determine the refractive indices, right? And so in this case, you know, I had to do that several times, and it was kind of a painstaking thing, but it was kind of fun. I won't lie. And then you've got the optical properties. We had a little bit of initial chemistry, and then that's about all we could do right there at the South Dakota School of Mines. So contacted Pete Dunn at the Smithsonian, and then other scientists like at Canadian National Museum, right? Say, hey guys, you know, we've got these new minerals. We've done this much, and we can't do any more. You want to help us out, right? So that's the process. So rarely does just one person ever work on a new mineral, right? It's usually a team of people, and they have their areas of specialization, you know, for the analytical methods. So that's what we did, and then you end up characterizing it, and then you end up publishing on it, right? And you name it, and you can't name it after yourself, okay? So you have to name it, like in this case, tiptopite. It was for the mine, the tip-top mine, pegmatite, right? And then the other one, one other one was pahasapaite, which is the Lakota term for the Black Hills, pahasapa, okay? And the other one, fransoletite, was someone that I met and befriended at a pegmatite conference, André Mathieu Fransolet from the University of Liège in Belgium. And his specialization was on primary phosphate minerals and pegmatite. So we honored him by naming that mineral after him. So that's how that process goes, you know, for finding and characterizing these new minerals. So it's kind of a fun and complex process. Okay, so back to the pegmatite part. So they're mined for economic concentrations of rare elements. So that would be like the tantalum, niobium, tin, beryllium, lithium, okay? Not so much anymore, mainly because there's different deposit types other than pegmatites that are larger volume, maybe lower grade that they can mine. But they still do. And the other part of it is gem rough and mineral specimens like these, right? So part of this process, and this is the economic geology part of this, really, is that, okay, these guys are mining these pegmatites, say in Brazil, and they actually do what they used to do 50, 60, 70 years ago. They stockpile concentrate of certain minerals, like the niobium-tantalum minerals will go into one pile, big black pile, right? Because that's what most of them are. They're just kind of black, sort of ugly minerals. I appreciate them. But anyway, and then like the lithium, so maybe big spodumene crystals, and then the giant beryl crystals. So they'll sort those out. And then if they're lucky, if it's a gem-bearing pegmatite, they'll have pockets, right, that they encounter during the course of mining, and maybe they find nice spodumene crystals in these pockets, or tourmaline crystals like that are over here, right, and aquamarines and whatnot. And so that's the other part of the economics for them. And so they have the material that can be processed for the raw material that it is, and then they have the gem-bearing material that they can use as and sell as specimens, or sell it as rough for gemstones, right? So that's how, this is not just in Brazil, this is anywhere that has pegmatite mining. So in Brazil, South Africa, Namibia, Pakistan, Afghanistan, Ukraine, anywhere that you have these gem-bearing pegmatites. As far as the chemical composition of them, they're very similar to granites. they tend to have a higher aluminum content, lower calcium content. The mineralogic and rare element pegmatites, again, are often enriched in sodium, lithium, rubidium, cesium, beryllium, boron, fluorine, hydroxyl, and phosphorus, again, which are important for gem minerals and economic mining. And something that we'll find out later on, some of these rare elements are concentrated during the fractionation process, and during that process, they actually, when they're in the fluid still, or in the melt, they change the properties of the melt in that, that fluid, and we'll talk about that. Give you an idea, okay, so I collect rare and unusual, I collect the pretty, you know, the aquamarines, tourmalines and everything, but I also very much appreciate some of the rare minerals. And this happens to be a really nice pollucite crystal. And so I don't expect everybody to know what that is, but it's essentially a cesium-bearing analcime, okay? Which is an analcime is a zeolite that you might be familiar with, but this has cesium in place of the sodium or calcium. So this relationship to granites. The pegmatites can be direct products of igneous fractionation from S-type granite, so they're the ones that are derived from melting of previous sedimentary rocks that have been metamorphosed and melted. And they're the offspring of these granite pegmatites. And this gives you an idea of what the texture of pegmatite is, very coarse grained. This has microcline quartz, a little bit of biotite in it, and some albite. And the depth that these pegmatites form are anywhere way below even 10 kilometers, so maybe 11, 12 kilometers up to near surface. And those are the ones that we're going to be interested in, as I'll keep talking about here. So these two diagrams, they're pretty classic. Peter Cherney, who was a good friend of mine, was a specialist in pegmatites at the University of Manitoba in Winnipeg. And so he went to a lot of pegmatite fields, and he mapped the relationship of pegmatites to the parent granite. And what he found out was that doesn't matter really how you slice it, whether you do this in plan view or in cross section, which this happens to be too. The zoning starts from the parent granite here, and you get essentially barren but coarse-grained pegmatites either within the granite or out in the metamorphic rocks essentially adjacent to it. And then you grade out into those that are that have beryl, so they're beryllium bearing, or those that have beryllium, niobium, tantalum. And then you might add lithium, and then the tantalum, niobium, beryllium, and then all the way up to cesium. So those are the ones that are more fractionated, and I'll talk about that in a little bit more detail. But this gives you an idea. And like in the Black Hills, I'll give you that as an example because it's close and it's something that's kind of near and dear to my heart. The Black Hills pegmatites around the Harney Peak granite are very classic in this regard. You look at it in plan view, you have the Harney Peak granite in the center, and you have these pegmatites that are found in essentially the metamorphic rocks around it, and it's zoned just like this. You just have to slice it in plan view, and that's what you get. You get the distribution of these pegmatites laterally out away from the Harney Peak, and that's the way it is in most places. You go to Brazil, Pakistan, the relationships are very similar.
On your other chart, what is the BTMS?
Biotite muscovite granite. So this is something that's a little bit more specific. So this is the zoning within the granite itself. So it might be a biotite granite at depth, biotite muscovite, a muscovite granite, and then more of a a pegmatitic granite up here. So here the grain size, you know, it might be, you know, average centimeters in size, whereas you get up into here, you're talking meters in size of the crystals, right?
So is that not a kind of a density differentiation there?
You know, it is a little bit, yes, because this material would be a little more dense and this would be less so. And that is part of the process that I'll get into about the emplacement of these. Yeah, yep, that's right, John. So we kind of talked about this. So the simple pegmatites are proximal to the granite, whereas the fractionated, the volatile bearing pegmatites are a little more distal, which we saw in that last diagram. And the rare element pegmatites intrude the country rock around the pegmatite. And you know, this is the evidence for the link between the pegmatites and that parent granite is supported by the geochemistry, okay, which we've kind of talked about. Age dating. So in most cases, you date the granite, say example, the Harney Peak granite. It's 1.72 about billion years old. And the pegmatites that are surrounding the Harney Peak in the metamorphic rocks are just slightly younger than that, right? So you can use age dating, and then you can use fluid inclusion work on the various minerals too to determine the microchemical link between the granite and the pegmatites. As far as size and shape of the pegmatites, they're variable. You can find pegmatites that might be the width of one of these tables, and it might extend for 100 meters. And you know, at depth, it might go for another 100 meters, whereas other ones are probably the size of this library, right? And I'm going to give you an example of a pretty spectacular one here in a minute. So the factors that affect the size and shape, though, are the depth that the pegmatites are emplaced, okay? The structures of the host rock, so they tend to follow, if it's metamorphic rocks and it's foliated, they tend to follow foliation, maybe shear zones or fracture zones within the metamorphics, okay? And then also the differences in lithostatic versus hydrostatic pressure. So what that is, so the lithostatic pressure is that load of all the rock above this, say this particular pegmatite. And the hydrostatic pressure is the pressure that pegmatite has on its own, because it has a certain amount of volatiles in it, and it has a certain amount of pressure in it itself, that hydrostatic pressure that helps it muscle its way into those metamorphic rocks. So if that pressure is higher than the lithostatic pressure, it will make its way upward. And the fact, like John was alluding to, it's almost a buoyancy thing too, right? The pegmatites generally are being emplaced into rocks. Well, they're much lighter. The pegmatites are much lighter and less dense. And they're getting emplaced into rocks that are more dense, right? So there's that buoyancy factor. So they can rise into those rocks with a higher density. And as far as shapes, they can be elongate dike-like bodies, dike complexes, big bulbous masses, inverted teardrop shapes, and these giant sheets too. And to give you an example, I put a little time in at the Tanco pegmatite at Bernick Lake, Manitoba years ago. And to give you an idea of how big this pegmatite is, it's one of the largest pegmatites in the world. It's 1,400 meters long, okay? 1,400 meters long. It's 600 meters wide and 100 meters thick. It's huge, right? And it has been mined for probably close to 40 years now. And life of mine is probably another 30 at least. And it's been a major source of cesium for the mineral industry, right? And so I'll go back to that one mineral specimen I showed you earlier, the palusite. That's what a lot of it's in. So yeah, it's huge. And then another example, this is the Helen Burl pegmatite in Custer, South Dakota. And this is really cool because it really is the exterior of the pegmatite here. So this is essentially the wall zone that's exposed on the surface. And then you have the intermediate zones, but then the intermediate zone and the core are mined out because that's where all the spodumene and the tantalum niobium minerals were, okay? And then again here for scale, I have my 7-foot wife there for scale. And that's my son, who, he was anomalous in size too. He's 7 years old and he was 4 feet tall. Yeah, okay, sorry. But it gives you an idea. Okay, so how do you classify pegmatites? Yeah, you can do it on chemistry, but when you're out in the field, when you're down in Brazil or you're in the Black Hills and say it was the early days and you come across a pegmatite or a series of pegmatites, you know, you don't have access to do the chemistry right then and there, right? So you can determine the mineralogy of each one, which helps. And then the other part too is with the mineralogy is the textures. And so if you come across pegmatites that have absolutely no pockets, and all of the pegmatites in that area don't have any pockets, you can definitely assume that they have been emplaced relatively deep into the crust. So we're talking probably say 7 to 11 kilometers at depth. So you don't have any pockets at that depth. So it's kind of like, well, I'll make an analogy here in a minute. But, and then as you go shallower in the crust, with more complex pegmatites, so you see the mineralogy here getting pretty complex with the lithium pegmatites and those that contain beryl, spodumene, maybe more albite, amblygonite, and other minerals. And then even closer to the surface, you get these mineralitic pegmatites, the ones that have pockets, and they have topaz, beryl, spodumene, petalite, lepidolite. And so, and these are the ones we're interested in, especially with respect to the minerals over there, okay? So the classification is a depth classification and a chemistry classification, essentially. And that's what they use now. And so there was a fellow by the name of Ginsberg in Russia and Peter Cherney. And then in recent years, it was Dave London and Skip Simmons, and they keep refining the classification based on a little bit more detailed chemistry, okay? So as far as depth, you know, and if you're a mineral collector, you know, do we want this, or would you prefer that? I'm going with the one on the right, okay? So as far as the incompatible elements go, and we've talked a little bit about some of these, you know, like cesium, and there's a couple groups here that we can talk about. The large ion lithophile elements that they call lilies. And so this includes cesium, rubidium, barium, lead, and strontium. And the ones we're mostly concerned with in pegmatites is the cesium and rubidium. And the high field strength elements, which include tantalum, niobium, phosphorus, zirconium for the most part for the pegmatites we're talking about. And the neat thing about it, and I don't have visual aids for this, but the cesium and rubidium, you know, their atomic size, their atomic radii, you know, it would be like having a basketball, okay? And it's very large and a +1 charge, okay? Then you have the high field strength elements like tantalum, niobium, phosphorus, zirconium, and even uranium. They're tiny, so it would be like a golf ball, essentially, okay? And very high charge, +5, +4, right? Well, those elements don't easily fit into the structure of common rock-forming minerals, right? Like the feldspars or quartz or micas, right? There's a little bit of substitution, but they don't form their own minerals with respect to the common rock-forming minerals. So, and even the pegmatophile elements, like lithium, beryllium, and boron. So what they do, they form their own minerals. So they don't substitute. They have limited substitution, but they form their own minerals, like the beryls and the spodumene and tantalite and columbite. And that's what's responsible for the unique mineralogy. And this is a specimen of wogenite that I have in my collection from Brazil. And so look at the chemistry of this. This is the formula. So it's a manganese tin tantalum oxide. Pretty bizarre, right? And forms its own mineral. Sorry, I had to throw this in there. So this whole thing, it's like a pegmatite soup, right? You have a lot of the common rock-forming elements as part of it. You have silicon, aluminum, oxygen, and potassium, sodium, and then you throw in all those oddball elements like cesium, lithium, beryllium, barium, boron, tantalum, right? And you just really mix things up in this pegmatite soup, and you end up forming these gorgeous minerals that are very unusual. And like here, this is a stibiotantalite with elbaite tourmaline and some albite. And my wife, Melissa, specializes in garnet, and this is a garnet specimen from Brazil. It's spessartine almandine, and some aquamarine from Arango, and a tourmaline from the Malkan pegmatites in Russia. So in this chart, I'm not going to go through the whole thing, but it gives you an idea of the complexity of the mineralogy in these rare element pegmatites and the pegmatites that can have these pockets, right? The mineralogic pegmatites. And so not only do you have the unusual chemistry that makes these minerals, right? Like beryl is a beryllium aluminum silicate. Tourmaline is a complex lithium aluminum silicate, borosilicate. And the neat thing about it is you might have just trace amounts of, say, manganese in tourmaline or in beryl to give it a pink color, right? So that trace amount of manganese makes these beautiful colors in the minerals. And I've got a neat piece of morganite beryl over there, and that's the pink variety. And then the pink portions of the tourmaline. So there's pink caps on a couple of the tourmalines over here. It's because of the manganese, right? Just a little bit of manganese in it. And then a little bit of Fe2+ gives tourmaline the green color. So like the bicolor tourmalines you see. So it's kind of a competition for iron and manganese. And I'm not going to go, I get really excited about this stuff, so sorry. But so maybe during the development of a couple of those tourmaline crystals over there, it's green for most of its growth, right? So there's more iron. When that iron gets depleted, and maybe there's a little bit of manganese left at the end and no more iron, and that's what gives you the pink caps, right? So just really neat things that happen in a pocket, a pegmatite pocket, as far as the chemistry goes. So there's a bunch of other gem-bearing and unusual pegmatite minerals on the side here, like Brazilianite, chrysoberyl, danburite, hamburgite, petalite, and phenakite, several others, just to give you an idea of the complexity, mineral complexity. So this is a diagram that's really good for showing the magnitude of concentration and the fractionation between a parent granite and the pegmatite. And I'm not going to talk about this one. This is mostly the source area here, but I'll let you look at those numbers if you want. But what I'm going to focus on, this is the parent granite here, coming off of this source area. And we'll focus on the lithium, cesium, beryllium, boron concentration that's in this parent granite. Lithium is at 57 parts per million, cesium 4, beryllium-4, boron-30. And you look over here, and this is in the fractionation process. So what happens is that these elements, along with some other of the oddballs we've talked about, they like going into this vapor phase that has water and a more buoyant melt, okay? And so, as we'll find out later, these melts can have up to 12% water in them, okay? And so these elements like that part of the melt. They like that vapor-rich portion, and they get fractionated into it. And so you get these concentrations like you see here. Lithium goes from 57 parts per million up to 3,450 parts per million. Same with cesium. You go from 4 to 2,600. Beryllium, 4 to 170. Boron, 30 to 215. And that's why you can get spodumene forming in it, or pollucite, or beryl, or tourmaline, okay? It's because those elements are fractionated into that part of the pegmatite melt. And so this is what happens. So you have this volatile enrichment that includes these, okay? I'm not going to read them off. But this is the cool thing. So this is essentially what happens due to the volatiles that are present in this melt. So and I'm not going to read these in order just because it comes from Simmons et al. And what I like to do is start, so from the kind of the middle there where it says decreases nucleation rates. So what happens is, whether it's the pegmatite or you're in a pocket, right? These volatiles, what they do is they reduce the number of places, say tourmaline, for example, will form. So instead of having a pocket where you have tourmaline crystals growing all over it, little ones, you have only specific sites where maybe a tourmaline or maybe an aquamarine crystal will grow. Instead of say thousands of potential sites, you only have dozens, okay? And so that's part of it. So it decreases the nucleation rates, and it also decreases the temperature at which these minerals will crystallize. That's at solidus temperature, right? And then it decreases the viscosity, so no longer do you have this super thick melt. It's, instead of being like molasses, it's more like maple syrup, the consistency, okay? And what that also does, it decreases the polymerization. So instead of having real complex chains within this volatile melt, it really simplifies it so that diffusion can increase. So if you have like boron atoms that are trying to make this tourmaline, it makes it easy for boron to get to these limited number of sites, right? And whether it's in a pocket or if it's in the pegmatite, it enables these crystals not only to grow large within the pegmatite, because there's only a limited number of nucleation sites, right? If it's in a pocket, it also enables them to grow large in the pocket, but also gemmy, right? Because they're growing in this restricted pocket that's fluid filled with a specific chemistry, and that's how you get those beautiful crystals forming in there, right? And you don't have, when you look at a pocket, and I'll show you a picture here in a little bit, you don't have, like I said, thousands of aquamarines or tourmalines growing in there, very limited number, okay? So that's what the role of volatiles does. Yeah, this is cool. This is an old picture from the Bumpus Quarry in Albany, Maine, and these are giant beryl crystals. So, and this was not uncommon back in the day when they were mining, right? So whether it was in the Black Hills, whether it was the New England pegmatites or the ones in Madagascar, yeah, they're giant crystals. And so they would mine these crystals and they would send these chunks of giant beryl crystals or spodumene crystals off to be processed, right, as a source of lithium or beryllium, right? And here again, I'm going to talk about that beryl from Madagascar. Okay, we said it was 18 meters in length. It was 3.5 meters in diameter, right? And it weighed 419 tons, right? Okay, largest crystal of any kind ever reported. So, this is kind of a summary. So, the role of volatiles. They exalt from the melt by fractional crystallization. The melts can contain up to 12% water. They lower the point at which minerals can crystallize. They're responsible for producing gem-bearing primary pockets, mineralotic cavities in these giant crystals. And they're also, sort of unfortunately, responsible for the corrosion and alteration of primary pockets in their minerals. So what I mean by that is, so if you have like a crystal of beryl, and you're welcome to come up and look at these. These pieces I have over here, you can handle all you want. These are all examples that I bring around when I do talks on pegmatites, and there's some cool pieces here. But so sometimes if you have a beryl crystal forming in a pocket and maybe the pocket ruptures, there's a fracture, and you have these other hydrothermal fluids coming from elsewhere in the pegmatite come in, it will actually alter the crystals that are in there, the previously formed crystals, which isn't a good thing, because that means you take a pocket filled with these gem crystals and you bring this other fluid in, and it will either etch them or alter them. And I'll tell you how that's done. And yes, this was a segue over to me getting my water. Okay. So as far as rates of crystallization, you know, most of us, when we were in college, we were taught that pegmatites, oh, you know, they have this coarse grain size because they took so long to form, you know, millions of years to crystallize, right? That's the way you got these giant crystals, right? That's what I was taught back in the day. So it's interesting. So within the last decade, people like Karen Weber, Skip Simmons, David London, they've been looking at pegmatites again, and they're finding out that the rates of crystallization are much faster than anybody anticipated. So they're doing these extensive studies, whether it's fluid inclusion work, or some of it is kind of commonsensical, but what they're finding is some of these pegmatites form in the smaller ones days to months, and then some of the larger ones maybe decades to hundreds of years. Okay, so it's not the millions of years that we're thinking of. Maybe in the case of a giant pegmatite like the Tanco pegmatite, maybe that's thousands of years. We don't really know yet, but my guess is those guys will probably be working on that at some point too, right? And the other thing that makes sense is that thin dikes cool faster than the big bulbous masses, right? You know, the dike complexes like the Himalaya pegmatite in California, you know, they're just, you know, a few meters to several meters thick. And it kind of makes sense that something like that, if it's intruded into the surrounding host rock, which is much cooler, it's not going to take thousands of years for that to cool, right? And when we're talking about those nucleation rates and the viscosity and everything, that actually promotes quick crystal growth, and the dikes probably didn't take as long as we used to think they did to form, right? So just something kind of interesting that I thought you'd, it's different, a departure from what we've learned. So pegmatite anatomy. The simple pegmatites, they're unzoned, generally not very economic, consist of feldspar, quartz, muscovite, and they pretty much have like uniform composition and texture, right? So there's no zoning, so it's mostly just feldspars, quartz, and micas. And the reason I say sub-economic is because sometimes those were actually mined for ceramics, right? You know, the feldspars, they'd mine the potassium feldspar for ceramics back in the day, or like isinglass, big sheets of mica to put in the fronts of the old furnaces and wood-burning stoves and whatnot, okay? So most of the shallow through intermediate depth pegmatites, they do have some kind of internal structure. And these internal structures, they're subdivided into zones, replacement bodies, and fracture filling units. And this diagram to the right shows the zoning pretty good. So you have the border zone, which is really essentially the contact with the country rock. So it's usually very fine grained. And then you have the wall zone, which is just inside that. Also, you know, could be variably, the grain size could be variable. And then you have the intermediate zone, but you could have multiple intermediate zones. And then you have the core right in the center, which a lot of times that's where, and I'll get into this, that's right at the core intermediate zone margin. That's often where you find these pockets in the shallow pegmatites. And it's also where you find, sometimes find these giant spodumene and beryl crystals too. Okay, the zones, they're incomplete to complete concentric shells. Okay, so they don't have to be perfectly concentric like I've shown here. You know, the wall zone usually is. And then the border zone and the intermediate zones, yeah, they might be continuous, but sometimes not. And then these are the fracture filling units here. And then the replacement bodies there is just as a diagram. So the interesting thing here is that each of these zones has a specific mineralogy. And when these pegmatites, they crystallize from the outside in. And when that starts happening, the core, the pegmatite, may be part of the intermediate zone. It might still be kind of a melt or a crystal mush, right? And as that pegmatite's cooling, like a lot of things, when it cools, it reduces in size and you get these cooling fractures developed. And you might end up getting material that was in the core or intermediate zone squirted into a fracture that transects the whole intermediate zone and maybe out into the wall zone. Okay, so you have something with a distinct mineralogy that is totally different from the host zone that it's in, right? And that's also a place where, by the way, where you can find gem crystals. Okay. So complex pegmatites, they're zoned, have fracture filling and replacement units. They're the ones that have the elevated concentrations of those elements. They're formed from highly evolved volatile-rich melts that produce pockets lined with these gorgeous gem crystals, okay? And these are a couple of really good diagrams. But the mineralogic pegmatites, the ones that have the nice pockets, they form between about less than a kilometer and a half to 3.5 kilometers. That's the sweet spot. That's the depth we like for these pocket pegmatites. And they're characterized by having pockets or cavities that have gem crystals, pods of pegmatite or pegmatite dikes that are located in the upper parts of parent granites and the adjacent host rocks. So that's the way it is in the Himalaya system in California. Cavities can contain crystals of quartz, beryl, tourmaline, topaz, along with feldspars, lyrosilicates, and other minerals. And these are, this is pretty good little schematic where you have essentially a graphic granite, very coarse grained, more of a pegmatitic graphic texture. And then you have the open space in here where you get these tourmalines and big quartz crystals and other mineral species forming. So their mineralogy, and I'll try to run through this pretty quickly. Silicates, phosphates, and oxides, they're the most abundant mineral groups. Most common silicates include quartz, microcline, feldspar, albite, and muscovite. And then you can also get spodumene, beryl, topaz, tourmaline, and garnet, common in some of these gem pegmatites. These are some examples of the silicates. So on the left side, my wife has graciously let me photograph her one specimen of cool specimen of spessartine garnet with albite from Pakistan. On the right-hand side, again, another one of these oddball minerals, petalite, which is actually a lot like spodumene. It's a lithium aluminum silicate, and it is also an ore of lithium. in some pegmatites. And then in the middle, this is actually a pretty spectacular specimen that Rob had and subsequently sold from Brazil. And you know, I never did get the dimensions on this thing, so I just said it's big, right? Sorry. But yeah, it was this tall, and it's almost like a polychromatic snowman, right? With a big albite base, and then it was a huge albite crystal top on there. Really neat piece. And then of course you get beryl on the left, and this is the green or yellow-green variety, Heliodor, and then aquamarine crystal from Brazil. And this one's from the Ukraine, and that's from Brazil. And then the one on the right, it's a topaz, beautiful topaz crystal on albite from Pakistan. And then the oxides, on the left here we have cassiterite, which is a tin oxide on albite. On the right, actually this is kind of cool, neat little story here. I got this on my last trip to Brazil. And so this is another one of those cases where I know this family, and I actually got to go in and actually map part of this pegmatite, the Itachia pegmatite. And he needed me to try to figure out the continuity of this zone that carried these wogenite crystals, because again, that's part of his economics, right? Yeah, the gem crystals, it also produces these beautiful tabular aquamarine crystals, but this is part of his economics too. He needed to try to find the extension of this wogenite zone so that he could mine that and use that material to stockpile for tantalum ore, right? Okay. So, and that's one of the pieces he had, and so I kind of like some of these black ugly minerals that come from pegmatites too. So I bought it, So anyway, interesting little story. And then a chrysoberyl, a six-ling twin here in the middle. I think those are fantastic. And that's a beryllium aluminum oxide. And then here we have some phosphate minerals on the left. This is fluorapatite on albite with a little bit of albite tourmaline. And then on the right, this is a gem monobrasite crystal, which is about 6 centimeters, really cool. And then the halides and borates. Yeah, you can find fluorite in a pegmatite, and this one's from Stocknala, and it's associated with some shoral tourmaline crystals. And on the right, I don't expect any of you to, you know what? Sometimes I bring incentives like candy to these things, and I ask people what the formulas are. I should have done that, I'm sorry. So anyway, I'm gonna ask you, anybody know what either behierite or sciavanitoite is? If anybody does, I'll tell you what, this is my incentive. Oh boy. And don't look at your phones. I'll give you $10 if you can tell me what either one of those is the formula. Okay, sorry, time's up. So behierite is a tantalum borate, and sciavanitoite is a niobium borate, two really rare minerals, okay? So yeah, there's just super unusual things that form in these pegmatites. And yeah, you're not going to believe this. Okay, we hear about zeolites, the ones that come from India, or the ones from here, whether it's in Wyoming or like up in Yellowstone. There's zeolite occurrences up at Yellowstone, right? And there's, if you go to Golden, Colorado, North and South Table Mountain, there's great zeolite occurrences there. There's some in Washington, right? And you think about those being associated with these lava flows or whatever, especially like the Deccan traps in India. They can form in pegmatites too. And it kind of makes sense, because why not? There's sodium, calcium, potassium, along with other cations, bearing aluminosilicates, and they just contain water, right, in their structure. So you can find zeolites in pegmatites. And even though unusual, and this piece here that we have, it's a spodumene crystal with a little bit of elbite and a big ball of stilbite. And this one's kind of cool too. It's kind of just one of those white minerals. But you have heulandite with bavenite, which is beryllium aluminum silicate. Okay, so you have these gem pockets. And what happens is you have this residual melt that accumulates and a low density volatile rich fluid exsolves that's rich in rare elements. And like I already said, the pegmatites crystallize from the wall to the core, okay? And the primary pockets are one of the last features to form during the crystallization of these. And they're the ones that contain these beautiful gem minerals, right? Well, and this is the interesting thing. So yeah, I'm talking about this stuff, but the size of these pockets, sorry, I tend to talk too much. But anyway, the size of the pockets, they can be this big, or they can be the size of that screen, or larger, right, in diameter, right? You can walk into them. And so that's how spectacular they can be and how large. And generally, they're found at the intermediate zone core margin. They're abundant in the shallow pegmatites, but essentially absent in the deeper, higher pressure zones of the crust. And this is just another schematic of a gem pocket. And a lot of times, the gem crystals can be preserved in clay, in pocket clay, and this can come from two sources. So as the crystals form within the pocket, you know, you get this residual fluid that keeps getting depleted in all of these elements that form, like the tourmalines or the beryls or whatever, the feldspars, right? And you just don't have much left in the fluid. You have all that material, all those elements taken out, and all it is, you end up getting or precipitating like a montmorillonite clay. There's nothing left, right? So you just crystallize this kind of a massive gooey clay in the center. And that can also happen the second way. That can also happen during pocket rupture, where you get those hydrothermal fluids come in, they break up the crystals, and then kind of the same thing. You just deplete the pocket in that material, and you just get a clay pocket that's formed that comes in later. Okay. Pockets are most common in complex pegmatites, but are rare. Pocket-bearing pegmatites that may be pervasive in some pegmatite regions like Brazil, Pakistan, Afghanistan, Namibia, Ukraine, Southern California, New England, they're still rare, okay? Pockets containing gem tourmaline crystals, aquamarine, kunzite, and topaz, like the pieces I have over there, are even more rare. You see where I'm going with this? Pockets are rare, and pockets containing preserved gem crystals are a miracle. Really, it really is. And this is a really cool diagram that Wendell Wilson, I don't know if any of you get the mineralogical record, but this is he's a great artist. And what he did for this diagram on the left is he took all the information he could from the Jonas pegmatite pocket and tried to put this together based on history, which included not only written history but oral history from some of the people that mined it and owned it, and put this together. And remember when I was telling you about limited nucleation sites and all those things that volatiles do? This is a great example. You can see that, okay, here was a nucleation site for these big crystals, right? Very limited number. It's not like the tourmalines were all over. They were very specific sites where those tourmalines grew, and they grew huge, and they grew beautiful. The tourmalines from this pocket were essentially a cranberry color, right? Very unique, very gorgeous.
Were the clear white and those just quartz crystals?
Yeah. Yep. Yeah, quartz, and then this is albite here. Sorry. Yep, that's quartz. Those are quartz. But a lot of albite and maybe some microcline. But yeah. So the occurrence of gem crystals. Pocket distribution is erratic, right? I'm not going to say that when you're mining a pegmatite, you know where these pockets are. You don't, right? And so like when these Brazilians, they're usually family operations for the most part, right? And they hire a few people. They don't know where these pockets are going to occur. So they have to mine with keeping the economic minerals in mind, you know, like the tantalum niobium minerals, the massive beryl, spodumene and whatnot, right? And if they happen to hit a pocket, that's just a bonus, huge bonus for them, right? But let me tell you, this is another short story. So what happens is that some of these families, they know how to mine out these pockets. They're very careful, right? So they'll take months maybe to mine out this pocket. Other people, other families that maybe aren't so experienced, and this is what happened one time when I went down there. This dealer gets a call from one of these families, says, we just hit this pocket. It's got all these crystals. Not all of them are on matrix, but we think we can reconstruct them. And that's what happens sometimes. They do. They have to reconstruct some of these. But can you send somebody down to evaluate it? So I get this phone call. Tom, can you go to Brazil? Can you check this out for us and evaluate this claim, right? And this pocket. So I go down there, I fly down there, great people, you know, nice family. They did have some interesting minerals that we ended up buying. And then they ended up sending me out to their pegmatite, kind of out in the boonies, right? And I've got a picture of it later. But I end up going down on this little electric winch, sitting on a log, right? And going down about 100 feet, and it's about 6 by 6. And you go down there, and we get down there, and it's great, you know, great looking pegmatite. They take me over to this place where the pocket was, well, where the pocket was, and this is where the pocket was. This is where we got all these great tourmalines. Oh, okay. And you took your time getting them out, right? Well, you know, we used a shovel and we used a rake. And I just went, oh, okay. And so they take me up, we go back to the house, and no kidding. They had 3 buckets, huge buckets, of tourmaline pieces. One bucket had all the terminations, the nice tips. Another bucket, they were pieces that were a little smaller, that they thought were the middle sections of the crystal. And then they had another bucket that they thought was the end, and then they had all these chunks of rock out here that they thought all of these things was going to be a giant jigsaw puzzle, and they were going to be able to put them back onto this matrix, right? And that's when I had to tell them, you know, I'm sorry, you know, it can't be done, right? And, you know, it's one of those things where it really takes someone with skill, and it's an art to be able to extract these crystals out of a pocket like that, right? Because, and this is what I told them, you know, I told them, you know, as far as gem rough, yeah, they might have had $500,000 worth of material there, right? But what I told them was, if you would have taken your time and extracted this, I said, you probably would have had about $10 million. And you see the jaws drop, right? But you know, it's an important lesson for them, right? Because next time, they're going to call somebody ahead of time and say, hey, we hit this pocket, what do we do, right? Well, it's using diamond chainsaws and being very careful in the extraction process, okay? So that's part of it as far as the pocket shape, and then the mineralogy of one pocket to another may be variable. So like you might run into a pocket, say over there where that table is, and it might have a certain mineralogy, and then you might end up running into a pocket right next door that has totally different mineralogy. Maybe that one has tourmaline and feldspar, like K-spar and albite in it, and this one might have aquamarine and schorl crystals in it, right? So real variable mineralogy. And so in larger pegmatites, the pockets are usually found between that intermediate zone and core area. More dike-like bodies, it's in what's known as kind of a pocket line right in the center of the dike, like in the Himalaya system. And these are, the pockets are dominated by feldspars, quartz, micas, and they're the ones that are rooted in the base of the pocket, and then you get the tourmalines and aquamarines and other topaz growing out generally on top of those, the quartz and the feldspars. And they like that open space. And like I said, and as we saw in that one diagram, the crystals aren't distributed uniformly within those pockets. Yeah, this is an awesome pegmatite specimen from a friend of mine, Carl Warning, on the right, from Stocknala. And can you imagine? So this was another one of those pockets where it was a few meters in diameter and had a limited number of these beautiful polychrome tourmalines in it, right? And so it was, this particular pocket had only a limited number of really good pieces in it, but that gives you an indication. And then this diagram on the left, again, kind of shows the relationship here. You got big feldspar crystals, a giant beryl crystal here, quartz crystals, tourmalines growing into the cavity, and then other tourmaline quartz crystals that might have been later, as in just really formed as floaters, or maybe formed as part of that pocket rupture process.
What would be the scale of that?
It actually almost whatever you wanted, John. Really, I mean, you could make it, you know, that, say this feldspar crystal here, that could be maybe half a meter, or maybe it's a meter, right? But it gives you kind of an indication of what these pockets might look like reconstructed. So again, and I'll just go over this real quickly, you know, the demise of these gem crystals. So when you have a pocket that has these gem crystals like an aquamarine, and it gets ruptured during the course of the pegmatite cooling process or some other process going on in the pegmatite, maybe that beryl crystal, kind of like at the tip top, gets attacked by fluids of a certain chemistry, and you end up forming a lot of these secondary minerals like bertrandite, euclase, phenakite, okay? And those might form at a certain pH and might be buffered by certain things. So this is how you form these secondary minerals after a pocket ruptures and those late stage fluids attack a beryl crystal. And that can go for spodumene or any other of these minerals. And here's a good example, like on the left, it's a elbaite crystal. It used to be an elbaite tourmaline crystal that's been totally replaced by lepidolite, and it's because of that late stage process, right? And then on the right, it's a beryllinite crystal, that big white snowflake, on a doubly terminated hydroxyl herderite crystal. Well, these are both beryllium-bearing minerals, and they formed as an alteration product of beryl, right? When these late stage fluids come in and alter a beryl crystal. So as far as the pocket condition summary, must have enough volatiles and favorable pressure conditions. Volatiles promote diffusion, limit nucleation sites, resulting in the larger well-formed crystals. Crystals grow into the open space. You have complex fluid chemistry and complex perigenesis, especially during pocket formation. Pocket rupture by internal pegmatite adjustments or maybe tectonic movements, might have mixed effects, as we talked about. And then clay filling may preserve or protect the pocket. Give you an idea of ages of some of these pegmatites that have pockets. So in general, granite pegmatites range in age between about, well, less than 35 million years and up to about 3.5 billion years. So the Pakistani pegmatites, about 35 million years. So my pointer won't work over there, but there's a really cool Pakistani aquamarine over there, and also a really nice elbaite tourmaline. So they are about 35 million years old, okay? Okay, and another example, there's a tourmaline crystal that's laying flat on the table up there from Pala. So that's from California. That's about 100 million years old. Okay? The pegmatites from the Orongo region in Namibia, about 130 million. The Chinese pegmatites in the Altai region, about 220. The Brazilian pegmatites in general average about 500 million years old. So a lot of the examples that I have over there from Brazil, about a half a billion years old. And then I have a Heliodor crystal from the Ukraine over there, big Heliodor. So the Ukrainian and the Black Hills pegmatites, unfortunately the Black Hills didn't produce the big Jimmy Heliodors or anything like that. But anyway, that Ukrainian Heliodor, 1.7 billion years old. Okay, that's the age of those pegmatites. And then the Tanco pegmatite that we talked about, that giant pegmatite, 2.6 billion years old. Okay, it gives you an appreciation of the range and age of these pegmatites, you know, through geologic time. And here's some interesting statistics, quote unquote, because they really haven't been tabulated, but less than 1% of all pegmatites are mineralogic. So less than 1% of them contain pockets. And less than 1% of these contain gem crystals and well-crystallized rare and unusual species. And less than 1% of gem crystal pockets survive intact. And here's an example of a pocket in the Himalaya mine where, you know, they were still able to extract the gem tourmalines as single crystals, right? And some of them were broken, some of them were misshapen and whatnot during the kind of the rehealing process and late stages of that pocket. But yeah, it essentially fractured the pocket, and so all of these tourmalines ended up being embedded in a clay. Okay. And this is kind of cool. So what you do, you know, you can't predict where the pockets are going to be, but what you can do is really just do some basic geologic mapping in the pegmatite, kind of if you know what you're doing, right? So you're looking at the mineralogy, and you're looking at the textures. And sometimes, and just very simply, so with the albite, you might see albite in this massive face that you're blasting into, kind of like this photo on the right, right? So you might see whether it's lepidolite or albite, and the albite changes from white to kind of a pale blue, and that's a really good indicator of pockets. Okay. The other thing is maybe you end up seeing biotite or muscovite, and then all of a sudden you start seeing lavender-colored lepidolite. Okay. So right there, those are two, to me, when I'm mapping, those are two indicators that say, okay, there's a possibility we might be coming up on a pocket here, right? So those are the kind of things that you do. And maybe it's changes in tourmaline color, maybe from schorl to elbite, you know, the green and pink. Oh, sorry. Maybe.
Woke you up, didn't I? So what he was doing, so I'm down in this Tachia pegmatite, and they blasted this round, and so what that is.
Go in and they're mining a tunnel, usually about 6 by 6 feet, right? They drill holes, load it with explosives, and then they muck it out, and they're looking for, you know, any signs of crystals. Well, at the bottom of this last round that they exploded, there was a small hole, right? And so what he ended up doing, what he was doing, was actually enlarging that hole, because we could see into it and we could see down that it got a lot bigger, right? And it's not one of those things you just take a sledgehammer to and do it. So he judiciously used, if you can do that with a small jackhammer, opened it up a bit, right? And then he ended up pulling out big pale citrine, so pale yellow quartz crystals out of that pocket. So it was really cool. So that happened while I was there, right? And so that's what they do. And then the other thing through the course of this, like I was telling you, they use those diamond tip chainsaws, and so they'll use those when they open a pocket up a little bit. Then they'll start using those just to cut pieces off that have matrix, so they'll have like albite with the tourmalines or the quartz crystals on them, right? And then they'll pack them up and prep them later. But these are some spectacular examples of pocket preservation and extraction, right? So these are the blue cap tourmalines, the famous blue cap tourmalines from the Tourmaline Queen mine in California. Really nice Himalaya specimen there in the center. And this is herderite crystals on topaz from Brazil. And some other very sculptural tourmaline pieces. And this one on the left is from Dunton Gem Quarry in Maine, and the one on the right is from Afghanistan. So those are, that's a big spodumene crystal with morganite, a pink beryl crystal. So, long, torturous life of a gem crystal. They must outlast the pegmatite and the pocket forming process. They have to survive late stage equilibration, fracturing in fluids, pocket rupture, etching, dissolution, alteration. You don't want that to happen, right? And then the waiting process. Will it outlast geologic time, right? And like I was saying, you know, say that Heliodor crystal over there from the Ukraine, 1.7 billion years. So that pegmatite was just discovered, I don't know, 5 years ago, but they've been mining those Heliodors for decades, right? But that's the thrill. It's kind of like breaking open a geode for the first time and seeing the quartz crystals in it, right? You're the first one to see it. So that's the neat thing about this. So they discover these, and it's been 1.7 billion years in the making, and this person is the first one to see those crystals that are in it, right? Yeah, so anyway, then will it survive the discovery and extraction process? Will it persevere packaging and transportation? Will it persist through the laboratory prep work and ultimately end up in display or placement in one of your collections, right? And here are some of those pictures from some of the adventures in Brazil. This is the one where I'm going down on the log into this little hole in the ground. And this is my good friend Gilarmando, who owns the Itachia pegmatite and the Araucum pegmatite. Okay, this one, here, sorry. We'll see if I can get this to play.
Aqui nós estamos lavando, jogando água, tirando o que está solto, para expulsar.
Okay, so these Brazilians, they just blasted into this large pocket, and it was several meters long, a couple meters high, and they were the first ones in there, right? And so Ronaldo ended up doing a video of this particular pocket. So I thought I'd share that with you because it's kind of interesting in terms of, you know, really seeing that initial discovery. And then some of the people that are responsible for the extraction process. Ramiro, wonderful guy on the right, or on the left, Ramiro Sardinia. And he has been mining in Brazil for 60 years, right? Ever since he was 20 years old or younger. And wonderful person. And he's been in on all the big discoveries down there. He was there during the discovery of the kunzites at the Araucum mine, the discovery of the Jonas mine pocket, and many others. And then Jill Armando on the right, and of course Bill Larson down there in the lower right. And so this is the summary. Based on the questions that we asked at the beginning, gem-bearing, rare element-bearing pegmatites are fractionation products of apparent granite. They're enriched in incompatible elements and volatiles that enable the formation of giant crystals, as well as pocket and gem crystals, if they're emplaced at shallow levels. Gem-bearing pegmatites can be less than 35 million years to 3.5 billion years old, have a diverse mineralogy ranging from sulfides to silicates. Pegmatite pockets are rare, and finding a pocket mostly intact is a miracle, and finding and extracting gem crystals from a pocket for collectors is definitely an art. And just in closing, and this is just my comments. Granite pegmatites are an intriguing igneous rock and mineral deposit type, and they represent an unusual combination of common and rare elements that combine to form diverse and beautiful mineral assemblages with complex paragenesis. And I study and collect pegmatite minerals for all those reasons, and because, to me, their artistry is manifested many different ways, not just in their appearance. It's the chemistry and how these things form. And then, really, above all, you know, it's the people that I've met along the way. You know, just some wonderful people in Brazil at the mineral shows. It's just been a great experience. But anyway, sorry, I didn't mean to go so long, but thank you for your time. And
So I think instead of our usual Q&A, I'd like to give people some time to look at the mineral specimens, and Tom will be there and can ask you a question. We have a small present, a token of our appreciation.
Oh,
And
thank you.
You could join me in thanking.
Pocket where it was hosted in carbonate, and the carbonate was dissolved, and
Actually, at the other table.
it's kind of like arsenopyrite. Okay. Yeah. So it's instead of arsenopyrite is iron arsenic sulfide, wallangite is actually a diarsenic sulfide. Yeah.
Where is that?
That's from China. There's a lot of interesting.
There's so many things.
There's a lot, as you'll find out from my talk. From Brazil, Pakistan, Afghanistan, South Africa, Namibia, the Ukraine.
Yeah. Get those
So many pegmatites. Yeah, I realize that.
This was back in the late 1800s, who just found outcrops right in the jungle and started digging on them and turned into these big mines, right? But the other way too was by placer deposits. So they found tourmaline in the river gravels, right? And they just like where the tourmalines were coming from, right? And back in the day, the green tourmaline in Brazil, they were looking for emerald, and that was what they were calling Brazilian emerald, right? Yeah. Until they figured out it's not emerald, it's tourmaline. I am Tom. Good to meet you. And that's my wife Melissa. Right.